Welcome to today's class. In the last class, we have seen noise equivalent bandwidth, noise equivalent temperature, and noise parameter called noise figure. In today's class, we are going to see narrowband noise and how to represent narrowband noise in terms of envelope and phase, and also in terms of in-phase and quadrature components. Narrowband noise, in short, we can name it as NBN. What is a bandpass filter? A bandpass filter is having a bandwidth in a band from Fc plus B to Fc minus B. So, to represent a bandpass filter in practical case, so this is our center frequency Fc and Fc plus B, and this is Fc minus B. So, generally we refer this as bandpass filter. And then what is narrow bandpass filter? The bandpass filter which is having a much smaller bandwidth than compared to its center frequency, then it is referred as narrow bandpass filter. So, what is a narrow bandpass filter? Narrow band, a bandpass filter, typically a bandpass filter which is having a bandwidth which is equal to 2 into B, which is much smaller than this bandwidth is much smaller than the center frequency Fc. Then this type of bandpass filter is referred as narrow band filter. Why it is important in communication system, in which part it is applicable? The receiver of the communication system usually includes, we know that, transmitter via a channel. The signal will be transmitted via a channel to the receiver. So, this receiver usually includes pre-processing of the transmitted signal. The pre-processor may take the form of narrowband filter. So, pre-processing in the form of narrowband. So, whose bandwidth is large enough to pass the modulated component, it will pass only the modulated component, but not large enough to accommodate the excessive noise. Therefore, it will pass the modulated component alone, and the remaining noise component and the unwanted signals will be filtered while passing through this narrow bandpass filter. The noise process appearing at the output of the noise process, appearing at the output of narrowband filter, NBN. In short, narrowband noise is referred as NBN. Noise process appearing at the output of narrowband noise is referred as, this is narrowband filter. It is referred as narrowband noise. Can we recollect what we have so far seen? What is a bandpass filter? Bandpass filter is having typically a bandwidth of 2B with a center frequency Fc. And then what is a narrowband filter? What is the purpose in the communication system? If we transmit a signal from transmitter to receiver via a channel, we need certain pre-processing in the front end part of the receiver. So, in the front end part of the receiver, we are having a narrowband filter which pass only the modulated component, and it will distort the remaining as that it will remove the unwanted filter noise components. The noise process appearing at the output of narrowband filter is referred as narrowband noise. So, to analyze the performance of communication system noise in this type of noise, particularly narrowband noise in communication system, we are in need of mathematical representation. So, we are in need of mathematical representation. So, depending on the applications, narrowband noise can be represented in terms of in-phase and quadrature component, and also in terms of envelope and phase component. So, we are going to see how to represent this narrowband noise in terms of envelope in phase and quadrature, and also in terms of envelope and phase. First we will see representation of narrowband noise in terms of in phase and quadrature components. So now we are going to see representation of narrowband noise in terms of in phase and quadrature component. We are going to represent N of t as narrowband noise. Which is having a bandwidth which is equal to 2b, centered at Fc. Center frequency is equal to Fc. Then in terms of in phase and quadrature component, N of t is equal to Ni of t cos 2 pi Fc t minus N q of t sin 2 pi Fc t. This Ni of t is the in phase component and Nq of t is the q represents the quadrature component. So now we are going to draw the extraction of Ni of t and Nq of t from N of t, that is analysis section and synthesis section for the narrowband noise. Assume this is our N of t. See, one of the input for the multiplier is cosine function, and here it is sine component. It is passed through the low pass filter. The output at the end of low pass filter is Ni of t, and this is the Nq of t. In phase component and quadrature component. This is referred as extraction of in phase and quadrature component from the N of t, or also it is referred as analyzer section. And what is the exact replica for the synthesis section? So we are going to take this Ni of t and Nq of t. We are going to combine this with the cosine component and sine component. After summing these two components, we will be at N of t, which is the narrowband noise. This is referred as synthesis section or synthesizer. Generation of N of t from Ni of t and Nq of t. Now we are going to see properties of narrowband noise. We are having 7 properties. We are going to see the 7 properties one by one. 7 properties of narrowband noise. First property is if Ni of t and Ni of always Ni of t and Nq of t have 0 mean. So this is our first property. And what is the second property? If N of t is Gaussian, then Ni of t and Nq of t are both referred as jointly Gaussian. Jointly Gaussian. What if an Ni of t is stationary? N of t is stationary, then Ni of t and Nq of t are jointly stationary. This is the third point. And if Ni of t and Nq of t have same these both, since it is having in same mean, 0 mean, the Ni of t and Nq of t have same power spectral density. This is the fourth property is Ni of t and Nq of t is having same power spectral density. And what is the power spectral density formula? Minus Fc and Fc, this is 0, Fc minus B, Fc plus B. Total bandwidth is 2B. It's referred as bandwidth. This is the power spectral density for the noise, power spectral density for the narrowband noise. This here minus Fc minus B minus Fc plus B. Therefore, what is the SNI of F and NSNQ of F? Both can be represented as Sn of F minus Fc plus Sn of F plus Fc within the bandwidth minus B to plus B and 0 elsewhere. Therefore, Sn of, what is Sn of F then? Sn of F is equal to Fc minus B less than or equal to F less than or equal to Fc plus B, and 0 for Fc greater than B, 0 for Fc greater than B. So, this is the power spectral density formula for in phase and quadrature component. So far we have seen 4 properties. The first property is in phase component and quadrature component is having a 0 mean. The second property in the narrowband noises, if our narrowband noise is Gaussian, then our in phase and quadrature component are said to be jointly Gaussian. And if our n of t is stationary, then our in phase and quadrature component are said to be jointly stationary. And the fourth point in the property is if n of t and nq of t are having the same power spectral density. Therefore, our in phase and quadrature component are expressed in terms of Sn of in terms of narrowband noise, Sn of F minus Fc plus Sn of F plus Fc. And fifth point in the narrowband noises, Ni of t and Nq of t are having the same variance as N of t. And cross spectral density of Ni of t and Nq of t are purely imaginary. Cross spectral density of Ni of t and Nq of t are purely imaginary. Therefore, our Sni and Nq of F is expressed in terms of minus of Snq Ni of F, or it can also be represented as J into Sn of F plus Fc minus Sn of F minus Fc minus B less than or equal to F less than or equal to B, and then 0 elsewhere. So, this is the sixth property in our narrowband noise. What is the seventh property? If n of t is Gaussian, Sn of t is symmetric about Fc, and then Ni of t and Nq of t are said to be, see, since we have mentioned here n of t is Gaussian and Sn of t is symmetric about Fc, then Ni of t and Nq of t are statistically independent. So, this is our first property, having a 0 mean. Second, Gaussian. Third is stationary. Fourth is both the in phase and quadrature component are having same power spectral density and they are having the same variance as that of the narrowband noise. The cross power spectral density are purely imaginary. And the seventh property is if n of t is Gaussian and Sn of t is symmetric around Fc, then Ni of t and Nq of t are said to be statistically independent. Just now we have seen the narrowband noise in terms of in phase and quadrature component. Now we are going to see narrowband noise in terms of envelope and phase component. In terms of envelope and phase component, n of t can be represented as n of t is equal to r of t into cos of 2 pi fct plus psi of t, where r of t is referred as the envelope of n of t, which is nothing but ni square of t plus nq square of t. This is the envelope of n of t, and psi of t is tan inverse of nq of t divided by ni of t. This is phase of n of t. The sample function of narrow band noise can be drawn as which is the sample function for narrow band noise. R of t and psi of t are both sample functions of low pass random noise. And another one representation for in phase and quadrature component and envelope and phase component is in terms of rectangular and spherical coordinate system. This incremental element is dni and this is dnq of t with respect to origin. This is ni, this is n, q, this is r, this is psi, this is d psi, and this gap is incremental length is referred as dr. This is in terms of envelope and phase. This is in terms of quadrature, in phase and quadrature. Representation in terms of in phase and quadrature and envelope and phase. Then R of t and psi of t are the sample functions of the low pass random process. Interval between two successive peaks, this R of t and psi of t are the interval between two successive peaks in the envelope R of t is 1 by beta. Therefore, our bandwidth is equal to 2b. The probability distribution of R of t and psi of t can be obtained from Ni of t and Nq of t, where capital Ni and capital Nq are represented as random variables obtained by observing the random process small ni of t and small nq of t, that is small ni and nq are nothing but the sample function. Therefore, the joint probability density function, joint PDF of the random variable capital Ni and Nq with respect to small ni and nq is, this is the random variable and this is the sample functions. Therefore, 1 by, since it is following the Gaussian distribution, 1 by 2 pi sigma square exponential of minus ni square plus nq square divided by 2 sigma square, and this is our equation number 1. It means that our random variable is lying between small ni plus gni. Similarly, our nq is lying in between plus gnq. Therefore, for the shaded area, the expressions are very taken from the Simon-Hankin's book Communication System. Therefore, for Ni and Nq of small ni, small nq, dni with respect to dni and dnq, 2 pi sigma square exponential of minus ni square plus nq square 2 into sigma square dni and dnq. This is for the small incremental area. We are taking this as equation number 2. Now, we are going to have the transformation. Small ni is equal to r into cos psi. See, in term r is equal to ni is equal to r into cos psi, nq is equal to r into sin psi. We know that cos is adjacent by hypotenuse and sin is opposite by hypotenuse. Therefore, NQ is equal to R into sin psi, Ni is equal to R into cos psi. Therefore, with the help of this transformation, the small one for also the small incremental area, for the small incremental area, dNi and dNq in terms of envelope and phase component, it can be rewritten as R into dr into d psi. Therefore, the joint probability density function, this equation number 1 can be rewritten as f of r comma psi small r comma psi is equal to 1 by 2 pi sigma square exponential of minus r square cos square psi plus r square sin square psi whole divided by 2 sigma square. We know that we can take r square outside, and in this cos square psi and sin square psi is equal to 1, since we know that by using the trigonometric identity cos square theta plus sin square theta is equal to 1. Therefore, this equation can be reduced to 2 pi sigma square exponential of minus r square divided by 2 sigma square. This is our equation number 3. From the in phase and quadrature component, we have reduced it into envelope and phase component, and similarly for the transformation, this one is reduced as transformed as in the representation of envelope and phase. Similarly, we have to transform the incremental area. Therefore, for the shaded area, f capital R comma psi small r comma psi into dr into d psi is equal to r divided by 2 pi sigma square exponential of minus r square divided by 2 sigma square into dr d sigma. See here, we already know that Ni square plus Nq square, this whole term can be reduced to minus of r square. Thus, dNi and dNq can be written as r into dr into d psi. This r is written here, r divided by 2 pi sigma square, and the remaining term from the above. So, this is the equation number 4. Here, since we have seen the probability density function is independent of the both the terms, the probability density function is independent of the first term. This is the probability density function, right? Joint probability density function. This is independent of psi component. It means that R and psi, that is envelope and phase component, are statistically independent. Therefore, we can rewritten this equation in the terms of R and psi are statistically independent. Therefore, we can rewrite this equation as, therefore, our expression f psi of psi can be written as 1 by 2 pi for 0 less than or equal to psi less than or equal to 2 pi and 0 elsewhere. Uniformly distributed, our in phase component is uniformly distributed from 0 to 2 pi. This f r of small r will be written as r by sigma square exponential of minus r square divided by 2 sigma square and 0 else. So, this joint probability density function can also be written as an probability density function for envelope and phase separately, using the property that both envelope and phase are statistically independent. F r comma psi of small, this f capital R comma capital psi of small r comma psi can be easily written as the product of f of psi into f psi of psi. Therefore, this equation we name it as equation number 5. This equation number 5 is said to be following the Rayleigh distribution. The graphical structure for normalized Rayleigh distribution is this is the peak value at 1 and this is 2 and 3, f capital V and small v. this with respect to V. What does small v stands for? Small v is equal to r by sigma. Therefore, we can represent in terms of normalized form f capital R of small r. Therefore, f capital V of small v is equal to v into exponential of minus v square divided by 2, 0. When we normalize this, equation number 5. This can be represented as equation number 6. So, maximum value at v is equal to 1. Unlike Gaussian distribution, Rayleigh distribution is 0 for non-negative values. Therefore, R of t can assume only the non-negative values. R of t can assume only positive values or non-negative values. Actually, this graph is supposed to be rise here and gradually drops to here. And the next we are going to see sine wave plus narrowband noise. The next topic is sine wave plus narrowband noise. If we add, what will happen if we add an sinusoidal component or cosine component to the narrowband noise? For example, consider a sine wave component is a cos 2 pi fct. So, if this is going to add it to the narrowband noise, if we pass this as an input, what will happen? We have to represent n of t in terms of, this is our input function. So, we are going to represent this whole term in terms of in phase and quadrature component. Assume this as x of t. Therefore, our x of t is equal to ni dash of, in terms of in phase, ni dash of t cos 2 pi fct minus nq of t sin 2 pi fct. This is in terms of in phase and quadrature component. So, this is our equation number 1, and ni dash, what is our ni dash, which is equal to a plus ni of t, our envelope amplitude of the cosine function plus ni of t. This is equation number 3. And what is we know that in phase component is Gaussian with a 0 mean. What will happen to then ni dash of t? Ni dash of t is also Gaussian, and ni dash of t and nq of t are statistically independent. It is going to follow the same property as that of the normal narrowband noise. Therefore, here the only difference is mean of ni of t is equal to a, sorry, ni dash of t is equal to a, unlike the ni of t is equal to 0. Mean of n q of t is equal to 0. And the variance of ni dash of t and nq of t are same. Therefore, that is equal to sigma square. Now, we are going to see the derive the joint probability density function for the normal area and also for the incremental area. Then, from the in phase and quadrature component, we are going to derive the envelope and phase component. The joint probability density function for the function ni dash and nq is given by f ni dash comma nq is equal to, small ni comma nq, which will be equal to 1 by sigma square exponential of minus of ni dash minus a. Since we know that ni is equal to, we already know that ni dash is equal to ni plus a. Therefore, our ni is equal to ni dash minus a. Therefore, plus nq square whole divided by 2 sigma square. We are going to keep this as equation number 3. Now in terms of envelope and phase component, we already know the transformation. R of t is equal to root of Na dash square of t plus Nq of t square, and psi of t is equal to tan inverse of Nq of t by Ni of t. This is the transformation from the in phase to the envelope and phase component. We are going to substitute here. Therefore, Ni instead of dash we can say prime also. Therefore, Ni prime of t is equal to R cos psi, Nq of t is equal to R sin psi. Therefore, by substituting the transformation functions are f, r comma capital psi comma small psi is equal to r divided by 2 pi sigma square exponential of a minus r cos psi whole square plus r sin psi whole square whole divided by 2 sigma square. So, this is our, this expression can also further reduce it to r divided by 2 pi sigma square exponential of minus r square plus a square minus 2ar cos psi whole divided by 2 sigma square. Here, unlike in the previous case, the envelope and phase component cannot be written separately because this r and psi component are multiplied together. Therefore, this joint probability density function cannot be written together as a separate functions. Therefore, f r of r comma psi of small r comma c cannot be written as the product function of f r of r and f psi of psi. It means that this both r and psi are dependent variables here, unlike in the case of previous. Dependent variables. Therefore, to determine the probability density function, that is in order to find the marginal density, we are going to integrate over 0 to 2 pi. Therefore, f capital R of small r is equal to integral over 0 to 2 pi f capital R small r psi into d psi. Therefore, this expression can be reduced to r divided by 2 pi sigma square exponential of minus r square plus a square divided by 2 sigma square integral over 0 to 2 pi exponential of ar cos psi divided by sigma square into d psi. This is the modified Bessel function. Modified Bessel function of first kind of 0 order. Therefore, this part can be rewritten as f capital R of r is equal to r divided by sigma square exponential of minus r square plus a square divided by 2 sigma square into I naught of ar divided by sigma square. Since I naught of x is equal to 1 by 2 pi integral over 0 to 2 pi exponential of x cos psi into d psi. This is the modified Bessel function of first kind of 0 order. Therefore, this equation number 4, this is following the Rayleigh distribution. In normalized form, it can be written as f small v is equal to v into exponential of minus v square plus a square divided by 2 I naught of av, where v is equal to small r by sigma and a is equal to capital A by sigma. This is the normalized Rayleigh distribution. Normalized Rayleigh distribution. The graph can be drawn as So this is for the small v, this is for f of v, marginal distribution. This is at a is equal to 0. At a is equal to 0, ration is equal to Rayleigh. Envelope distribution is approximately Gaussian in the vicinity of v is equal to a. This concludes our third unit.